Okay. Good afternoon and welcome to today's theoretical physics seminar. Today's speaker is Dr. Suddhasattwa Brahma of the University of Edinburgh at the Higgs Center for Theoretical Physics in the University of Edinburgh. Dr. Brahma works mainly in the field of quantum cosmology. He did his PhD from Penn State in canonical quantum gravity and then did postdocs at the Fudan University, the Asia Pacific Center for Theoretical Physics in Pohang, and then McGill University. Now he is Higgs Fellow at the University of Edinburgh. He is currently visiting the city, so we thought we would get him to speak here in person. But since then, we have had new COVID-related regulations, so we have had to go with an online talk. The title of his talk is From Abstract Matrix Models to Observations in the Sky. Suddhasattwa, the floor is yours.
Thank you so much for the invitation. And thank you so much for the invitation. And yeah, it's a pity that I have to do this online because of all the regulations now. I'm very glad to be here, nevertheless, and be able to present my work. I hope you can all hear me and see my screen. Is my cursor visible as well?
Yes.
Okay, thank you. So yeah, please stop me if something is unclear. I'm happy to just stop and answer questions. And I would rather go over less stuff and be clear than go over everything. Okay, so what we are interested in is answering something like this, what happened in the very early universe, and that's what interests me. Or for the purposes of this talk, that is what I'm going to talk about. And of course, the standard answer to that question is don't we already know? Because there's this standard paradigm of inflation, which is to say that you take a tiny patch of space and you blow it up to make it the entire observable universe. So there's this early phase of accelerated expansion, and this is the standard paradigm in cosmology. And this answers what happened in the very early universe. Just to make this even more rigorous, and I should mention that I'm going to be very introductory, and I apologize to cosmologists in the audience if I'm repeating stuff that you're already very familiar with. So inflation not only solves standard cosmological puzzles, and I'm going to talk a little bit later about what these puzzles are, but it also does something more. It explains late-time inhomogeneities as we see as anisotropies in the cosmic microwave background. So it explains these late-time inhomogeneities as originating from quantum vacuum fluctuations. So this is a remarkable achievement of inflation, that it not only solves certain puzzles of standard Big Bang cosmology, but it can explain large-scale structure, essentially, originating from quantum vacuum fluctuations. However, inflation is past incomplete. This essentially means, heuristically, it means that we don't know what came before inflation. We can't have infinite inflation in the backward direction in times, if you would. So this is a mathematically rigorous statement that was proved by Bourdet and Guth in 2007. The reason for emphasizing this is that there is this paradigm of eternal inflation, which means that inflation might be eternal in the future, but nevertheless, it must have a surface on which inflation began. You can't have inflation go all the way back to the Big Bang, so to speak. So again, this is a cartoon to illustrate this point, that there was this Big Bang singularity, and inflation certainly does not take care of this. And this cartoon on the right sort of illustrates that, the smooth space-time continuum that we know might actually have some very fluctuating quantum atoms of space and time to begin with. And this is something that we are that we cannot answer if we just look at inflation. So if inflation had to begin at some finite time, it's only natural to ask, what are the initial conditions for inflation to begin? Again, what I mean by this is, let's look at this very standard cartoon that inflationary cosmologists often refer to. And this is showing the potential of some scalar field. And the idea is that the inflaton rolls over a very flat region of the potential, such that this gives you all the slow roll inflationary dynamics that you need. And at the end of inflation, there is some reheating because the field goes to some local minimum or some minimum, and then there's some oscillations around this minimum, and this produces all the particles that we know today. Now, a natural question to ask is, why was the field, to begin with, displaced from the minimum? Why was the field slow rolling on the flat part of the potential and not already at the minimum? Again, just to emphasize the sort of deep theoretical mystery behind this, we can't simply have a very flat potential throughout, because if we did have something like that, then we would never be able to end inflation. So there must be some sort of a minimum nearby in order to exit inflation. This is the graceful exit problem. And if there is such a minimum, then why was the field displaced from it to begin with? And this is something that has to be answered. And this inflation by itself cannot answer this question, simply because it's a finite time at which it began. So what I'm hinting at is there some UV completion of inflation? Can we resolve the Big Bang singularity that we see? Because as I mentioned, we can't do that within inflation. And what are the initial conditions? And the only way to do this is to look at some quantum gravity theory. In other words, can we derive inflation from something more fundamental? And I think the only serious contender for a fundamental theory of physics is perhaps string theory. So in this sense, can we embed inflation in string theory? That's what I would mostly try to motivate and answer in this talk. Now, a slightly more philosophical point is that in the early universe, there are two approaches to doing early universe cosmology. One is what I would call a toy model approach, in which you say that it's very difficult to start with the full quantum gravity theory and then try and get cosmological dynamics from it. So what instead people do is that they look at simplified models which are inspired somehow by quantum gravity. And a classic example of this is loop quantum cosmology, in which you start with some simple cosmological model and you quantize that model using techniques of loop quantum gravity. So this is not quite a derivation of cosmology from loop quantum gravity. Rather, this is, let's look at a simpler system classically and then try to quantize it using ideas from loop quantum gravity. So this is one way to go about doing early universe cosmology. And the only reason why people do this is because it's very difficult otherwise to make any progress. And I'm not running this method down, but I'm going to advocate the other way, which is to say that let's do a top-down derivation. So let's look at some full theory of quantum gravity and try to extract its cosmological dynamics. Now, this is very difficult because let's again take the example of loop quantum gravity. In loop quantum gravity, the fundamental degrees of freedom are things that are exotic things like spin networks. These are abstract mathematical concepts. So how do I extract a cosmological scale factor from it? How do I extract observables from it? How do I match it with anything that we see in the sky? So that is a very difficult thing to do. And it's certainly extremely ambitious to try and start with a full quantum theory of gravity and try to extract its large-scale cosmological dynamics through some coarse graining. But that's what I'm going to advocate in this seminar today. And what would help us a little bit is this recent idea of the string swampland. So the idea here is that there are very strict theoretical consistency conditions which any effective field theory must satisfy in order to be able to have a completion in quantum gravity. So in order for an effective field theory, which otherwise looks perfectly healthy, to have some completion in quantum gravity, to be able to be derived from quantum gravity, it must satisfy some theoretical consistency conditions. And the swampland idea was that it identifies universal features of UV complete early universe scenarios. I mean, it identifies universal features of any UV complete theory. The one that I would focus on are those which are relevant for early universe cosmology. And what is interesting is that the swampland program has recently pointed out several obstructions for inflation. So what might happen if one goes around trying to derive some cosmological dynamics from string theory, for instance, one would probably find some early universe cosmology, which is maybe not inflation, but might still be consistent with observations and so on. That's the hope. And of course, this is a very, as I mentioned, this is a very ambitious goal, because we are trying to start with, string theory or some other quantum gravity theory, and we are trying to rewrite the rules of cosmology. In some sense, we are trying to do a new standard model of cosmology, but with high risk come comes high reward. And the reward is that now we will get some testable predictions for quantum gravity. Because we have precision cosmology with us today, we have a lot of data with a lot of observation, and this would give us falsifiable predictions for whichever quantum gravity theory I begin with. So the take-home message, if you fall asleep after this slide, is that I'm going to try and motivate an alternative description of the early universe from what is known as the Bfss matrix theory. And without knowing any details about this theory itself, what I can tell you is that here the fundamental degrees of freedom are matrices. So these are very abstract mathematical concepts. And I'm going to extract cosmological observables such as the power spectrum and expansion rate and things like this from this matrix theory. I'm going to show you how one is able to do that through suitable coarse grainings. And that's going to be the topic of this seminar, a new description of the early universe coming from Bfss matrix theory. Why is this theory interesting? Because this is a proposed non-perturbative definition of M theory or string theory. So this has very close links with string theory. So that's why we choose this theory to begin with. Any questions? Sorry, I can't see anyone. So please, if you're raising your hand, just interrupt me and ask any questions. Okay, so before I go on, let's just do some basics of cosmology. So standard Big Bang cosmology explains successfully a lot of things. For instance, the expansion of the universe, which is given by Hubble's law, the existence of the CMB, that is already explained by standard Big Bang cosmology, and the abundance of light elements, which is the Big Bang nucleosynthesis. These are all explained nicely by standard Big Bang cosmology. However, the shortcomings of standard Big Bang cosmology are also quite well known by now. I mean, this is something, a graduate course in cosmology goes over like in the first lecture or something. And I would refer to this nice review by Daniel Bauman from 2009 on inflation to look at the shortcomings of standard Big Bang cosmology. And the shortcomings are this so-called horizon problem, the flatness problem, and the singularity problem. So I've already mentioned about the singularity problem. Inflation doesn't solve the singularity problem. What are the horizon and flatness problems? So I'll just go over one of these, and the other one would probably be clear already. So the horizon problem is that if you look at the CMB, and we can calculate how long after the Big Bang singularity was the CMB formed, and then we look at two different parts of the sky, then we can...
There is some disturbance in...
What region was in causal contact with one part of the background? Oh, sorry. Can you hear me?
Yeah, there was a little disturbance.
There is no noise in my background. Can you hear me now?
Yeah,
No.
we can hear you, but there was a little bit of a disturbance for a brief while.
Am I audible?
Now you are. You are audible now,
Okay,
but we missed about a minute.
Okay. All right. So the horizon problem is simply stating that if we look at the CMB, the cosmic microwave background, and we look at two parts of the sky, then one point in the sky, which is opposite, let's say, to another part of the sky, the region which was in causal contact, the region to its causal past were never in causal contact at any point. So this is to say that two parts of the sky that we observe in the CMB were never in causal contact if we just look at Big Bang cosmology. And if that's true, if standard Big Bang cosmology is true, then why is the CMB so homogeneous? Why is the CMB so isotropic? Why is the anisotropy in the CMB so small if things were never in causal contact to begin with? And this is the horizon problem. And standard Big Bang cosmology cannot solve this. But of course, this is an extreme initial fine-tuning problem. One can just say that, every point in the CMB is just similar to each other for no good reason. This is something that I ask by fiat, and I don't want to give a causal interpretation to it. That's very unsatisfactory, because then a lot of the sky, anything above 6 degrees or 4 degrees, something like this, would not be in causal contact and yet looks the same to us. Why is that true? The flatness problem is something similar. Why is the spatial curvature of the universe so small? And if it is small today, then it had to be very, very small to begin with. And again, this is another initial fine-tuning problem. We can just say that, the curvature of the universe is 0 to begin with, but that's setting it to 0 by hand. Why should I do that? Is there a causal mechanism which can solve this? And this is what I write down as the wish list of an early universe cosmologist. So the wish list is that we want to solve the standard horizon problem. We want to explain the origin of structure. This I already mentioned. Inflation explains the origin of structure as coming from quantum vacuum fluctuations. And we want to derive everything from a fundamental quantum gravity theory so that we get rid of the Big Bang singularity. Now, the solution of the standard horizon problem, all it requires, and what I'm trying to do here is, get away, as far away from inflation as possible, and tell you what is the minimal requirement in order to solve these problems. So to solve the standard horizon problem, what we need is the Hubble radius is smaller than the causal horizon at some point. That is all that is needed. Again, this is a nice review which goes over this point. Now, inflation is a way to do this, but inflation is not the only way to do this. All we require is the Hubble radius is smaller than the causal horizon at some point. For deriving the origin of structure, all we need is that the scale invariant power spectrum of adiabatic perturbations, the power spectrum of adiabatic perturbations is scale invariant. Again, inflation is a way to generate scale invariant power spectrum, but that's a mechanism to generate scale invariant power spectrum. That's not a necessary condition. And just to emphasize this point, please notice the date on these papers. So these gentlemen were the first to show that if I assume a scale invariant power spectrum, then we can explain the origin of structure. And the date on this paper is 10 years before inflation was introduced. Inflation was invented. So this is the figure from one of these papers from 1970. Again, inflation is the first scenario which gave us a causal mechanism to generate, which told us how we can generate scale invariant power spectrum. But what I'm trying to emphasize is that all that is required is that you need a scale invariant power spectrum. It doesn't matter how you generate it. Inflation is one way to do it, but there may be other ways. And this was already known in the 1970s. Okay, any questions?
It's okay. Please go on.
Good.
No questions.
What I'm going to advocate is that you need to look beyond the effective field. Please. I think there's a lag, right? I'm listening to you a little while later.
Yeah, now it's back. Yeah.
Okay, that's good. So what I mean by beyond EFT of inflation is that we have, so when I write down the action, I write it down as the Einstein-Hilbert action of GR plus some minimally coupled scalar field plus some potential term as I require for inflation. Now, the idea is that if you have an EFT of inflation, then as you go to higher and higher energies, you add higher and higher order terms. And what I'm proposing is that this kind of an approach would fail at some point. You cannot keep on adding higher order operators and hope that you capture the physics of the early universe. This is just not possible. And you need some dual description. And a way to see this is as follows. So now inflation tells us we all know this often quoted number of 50 folds or 60 folds. This is the minimum amount of inflation one must have in order to solve the horizon problem, the so-called horizon problem, which I just mentioned. In order to solve this problem from observations, we need at least this amount of inflation. But how long can inflation last? This is a minimum requirement, right? I mean, this is a lower bound that we must have this much inflation in order to solve observations. But how much inflation can we have? There is no observable bounds on this. And indeed, most common models of inflation have 500 e-foldings or 1000 e-foldings and so on. And the question is that the interesting thing is that the string swampland has recently has shown us that from various considerations of string theory as well as other things, what is allowed is perhaps only very short-lived metastable de Sitter vacua. And I just mentioned this de Sitter vacua, but I mean, this is true for any accelerating background. So even if you're allowed to have accelerating backgrounds, they must be very short-lived. And this is what the string swampland is telling us. And if this is true, then what that means is that even if inflation is the early universe paradigm that was there, it has to be very short-lived. Now, short-lived inflations have many problems. So let's say the inflation is like, can live 37 e-foldings or something like this. That means that the energy scale of inflation, in order to solve observational issues, has to be very, very small. And such low-scale models of inflation essentially then gives rise to fine-tuning issues. So again, this is a cartoon to illustrate that we know how much inflation we must have. I mean, how little inflation we must have. We don't know how much we can have. And only a theoretical consistency condition can give us something like this. So if my internet is not very good, maybe you can just stop my video, because I feel like you're hearing me a little late. Is that okay?
We can hear you, and we did see the picture before this. So
I'm just stopping my video, and I will go back to my screen.
Okay. So I actually had a question about this.
Okay, perfect. Please go ahead.
So what I was saying is that I was under the impression that most string vacua are radius, right? So now
That's
you
right.
are saying that swampland implies that short-lived metastable DS vacua can exist, but how does it fall into this DS vacua? I mean, if most of string theory has ADS vacua, how does it get the DS vacua?
Right. So I'm with you on this one. So I'm actually saying that the swampland in its strictest version says that you can't have de Sitter vacua, you can't have inflation. I'm actually saying that there are some milder criteria which says that maybe you can, but even if they exist, they have to be very short-lived. So of course, there is a possibility that the swampland just rules out inflation. That's entirely possible. And that's probably what it says in its strictest version.
I thought that was the original conclusion.
That was the original conclusion, but then since then there has been a lot of refinements. People have tried to say that, requiring less and less things, how much can we show rigorously? And what we can show rigorously sort of is that even if de Sitter is there, it has to be very short-lived.
Short-lived means what?
Short-lived means it has to be around a scrambling time of de Sitter. So it's like 1 over h logarithm of h, something like this.
Okay. Yeah, please go.
So this is another motivation for this short-lived de Sitter vacua. So of course, again, as very rightly pointed out, I mean, probably de Sitter vacua are ruled out, and that's what I'm mostly advocating. But I'm just trying to be as minimalist and as less of creating as less controversy as possible. So I'm saying that maybe there is de Sitter vacua like KKLT, but they have to be very, very short-lived. And inflation maybe is compatible, but it has to be very short-lived. And this is another argument for that from the Transplanckian censorship conjecture. Now, I don't want to get into the details of this, but the idea here is that this is the beginning of inflation. Ti marks the beginning of inflation. So the vertical axis is time and the horizontal axis is space. Ti is the initial time for beginning of inflation. Tr is the end of inflation. And what we require, and this is the horizon in the sky today. For inflation to explain the observations in the sky today, the horizon today must have originated from within the horizon, from within the Hubble horizon at the beginning of inflation. So this is the Hubble horizon, which is almost constant during inflation. And this is standard Big Bang cosmology. So any physical wavelength in the sky today, which demarcates our horizon today, must originate from within the Hubble horizon at the beginning of inflation. And this is the Transplanckian censorship condition, which is saying that any Transplanckian mode, which means that any mode which has its wavelength smaller than the Planck length, which is given by this red zone. So this is the danger zone. So anything that has a wavelength smaller than Planck length should not be allowed to exit the Hubble horizon. Now, why is this the case? Is because everything that exits the Hubble horizon classicalizes and becomes macroscopic perturbations. And this is not what we want, because Transplanckian modes, I mean, we don't know how to deal with it, but at least if it doesn't exit the Hubble horizon, And this is why this is a minimal requirement. If it doesn't exit the Hubble horizon, then it remains quantum and we don't have to worry about it in the classical observations. So of course, there might be some more stricter conditions on trans-Planckian modes, but this is the most mild condition that we can impose on it, that it should not exit the Hubble horizon and classicalize and become part of our observation. And this gives us an upper bound on inflation. And this upper bound is such that you find that inflation has to be very short-lived, and this gives rise to a lot of fine-tuning issues. Okay, so let me just, this was all sort of motivation and arguing against an EFT of inflation. And let me summarize this part, which is we don't know if inflation is true, then we have to answer the question of what is the origin of the inflaton. We have no idea about this. What gives the inflaton field? The standard Higgs field certainly doesn't do that job unless you allow for non-minimal couplings and all sorts of weird things. So we have to go to string theory and things like this to explain the origin of inflation and the inflaton. Now, in some sense, the end state of quantum gravity is the initial state for inflation, right? Because you have a quantum gravity era followed by an inflationary era. Now, this is not just a philosophical statement. This is something that has observable consequences, because if the end state of quantum gravity for perturbations is not the Bunch-Davies state, that gives explicit observable signatures. So it is important to work out what is the end state of quantum gravity, even for observations. And as I mentioned earlier, inflation as an EFT, an effective field theory of simple scalar degrees of freedom with higher and higher order terms added to the Lagrangian, simply does not work. And that does not work because if you keep doing this, if you keep adding higher and higher order terms as you go to higher and higher energies, if this picture was true, then we should be able to write down the string Lagrangian just starting from some low energy EFT. And that is precisely what doesn't happen, because what you're finding is that long-lived de Sitter spaces, or the kind of popular inflationary models like M2 phi2 potentials, these kind of models do not have string decompletions. They cannot come from string theory. So what we need in order to embed inflation or quasi de Sitter space in string theory is to go beyond EFT. Even if we are to have some accelerating space-time, we need to go beyond such an effective field theory approach. And this is something that I haven't talked about at all, and I will not go into any details. But you can see this even from quantum field theory arguments and not going to string theory. So what we did in a paper recently with Robert and a master student at McGill is that we calculated the entanglement entropy of cosmological perturbations. So we split the space of cosmological perturbations, the momentum space of cosmological perturbations, into observable modes and things which we cannot observe, so high energy modes. So things which have never exited the Hubble horizon. If we do this and calculate the entanglement entropy between these observable and unobservable modes, we find something remarkable. What we find is that the entanglement entropy for any accelerating space-time, namely inflation, increases at a rapid rate. It increases so much that even though this is a perturbative quantity, this entanglement entropy is a perturbative quantity, it can overcome the Gibbons-Hawking background entropy at some point. And the time for this perturbation theory to break down, or whenever this perturbative entanglement entropy overcomes the background entropy, is precisely the same time that one calculates this scrambling time, or this TCC time, this trans-Planckian censorship time, as one calculates from string theory. So this is quite remarkable. We are doing a calculation for QFT on accelerating spacetime, nothing to do with quantum gravity or string theory, and yet we come at a time scale after which the theory cannot be trusted, which is exactly the same time scale which one derives from string theory for the lifetime of de Sitter. And this is what we showed in a recent paper. So there are multiple evidences that you can't have long-lived de Sitter vacua or inflation for long. I mean, which has to have some consistency requirements satisfied. And this is what I wanted to focus. I wanted to emphasize. So for a consistent realization of inflation, it has to be derived. Sorry, yeah, there was a question. Please go ahead.
I just wanted to ask that this entanglement entropy that we have computed,
yes,
is the von Neumann entropy.
That's right.
Okay.
That's right.
I mean, just a little bit confused. Is you're computing this at finite temperature, right? This cosmological perturbations, there must be a temperature here.
Right.
No,
No, this is okay. So typically, yes, of course, there's a temperature here, but remember that. So we are assuming inflation in this case, right? So the background is given by inflation. So the perturbations are quantum vacuum fluctuations.
Okay, so only one small remark is that this von Neumann entropy at finite temperature, one can calculate the von Neumann entropy, but then it is not a very good measure of entanglement entropy at finite temperatures. It's a
That's right.
measure of entanglement entropy at zero temperature.
That's right. That's right. I completely agree.
Yeah, but then is it fair to calculate, say that it is an entanglement entropy of cosmological perturbation, or it is something else completely?
Right. So let me. So there are two things here. One is whether this is fair to ask the question whether it's entanglement entropy. So let me answer this in two ways. First of all, I really am not so worried whether this is entanglement entropy or not. What I'm trying to motivate here is that there is, so in standard Wilsonian theory, we always do Wilsonian renormalization and we integrate out high energy modes, and we can just work with the low energy observable modes. That's perfectly well defined. But in inflation or in cosmology, this is not so well defined, simply because you don't have time translation symmetry. So you can't just integrate out high energy modes and be done with it. So another way to think about this is, gravity is non-renormalizable. So if you have accelerating background and if you have a short wavelength mode at some time t, at some later time, that mode will be stretched and redshifted and it will become part of your system. So what we are saying is that let's just consider all the modes which will never cross the Hubble horizon, and this is our unobservable modes. And let's just calculate what is the entropy because of interactions between this unobservable and observable modes. What is the von Neumann entropy? Now, this is not finite temperature calculation, because for inflation, inflation is supposed to do the opposite, right? It's supposed to say that you have even if you start with some big bang and you have some high temperature state or whatever, inflation dilutes everything and it makes things go to zero temperature, and then you must have reheating to get back the finite temperature bit. So what we are saying is that this is just a calculation of momentum space entanglement entropy for a scalar field which has some cubic interaction. Instead of on flat space, my background is given by inflationary space. Now, if this is not entanglement entropy, that's not particularly of worry to me. This is just some measure of entropy. And all I require is that this entropy must never overpower the background entropy, because this is still quasi de Sitter.
In any case, it is entanglement entropy now, as you say, because you are computing this at low temperature. So then there is no problem.
Right. Yes, that's the idea. And the point is that if one does this for flat space-time, then we know how the entanglement entropy, this is very well known. I was quite surprised that nobody has calculated this kind of entanglement entropy for curved space-time. Curved meaning curved for accelerating space-times. And this kind of calculation tells you that accelerating spacetimes give a very weird notion of entanglement entropy. And this has a lot of puzzle. I'm not going into this topic because this has a lot of potential for solving the page curve and things like this. And people have studied this for black holes, but not so much for de Sitter spaces. So this has a lot of potential in that direction. But I'm happy to discuss more at the end. I don't want to get into this. Okay, so that's the upshot, is that we need to go beyond the simple effective field theory description of inflation. We need to do something more. We need to start with a more UV complete theory and try to derive some cosmology from it. And I've motivated enough about alternatives. Are there any alternatives to inflation? And already there are quite a few alternatives to inflation that are well known. One is this string gas cosmology, which is shown by this figure on the left-hand side. As I already showed you, this inflationary figure, how inflation can give you, can solve the horizon problem. Similarly, this tells you how string gas cosmology, which was developed by Robert and Kamran Waffa in 1989, this solves the horizon problem. This is another approach coming from string theory, where you consider a box of strings, and a box of strings, the thermodynamics of a box of strings is different from the thermodynamics of a box of point particles, and that's why you can have a scale invariant spectrum and solve all the standard cosmological puzzles that I mentioned. I won't go into the details because this is not very relevant for my talk. There is Pyratic Bounces, which was developed by Neil Turok, Paul Steinhardt and collaborators. And very recently, Kamran Waffa came up with another idea known as this early phase of topological gravity. I'm just mentioning these names. You don't have to know the details, just to say there are alternatives in the market. But again, that doesn't mean that these alternatives don't have problems. They themselves have many problems, just like I pointed out problems of inflation. these also have several problems, which I'm not going into. So this is not to say that they do any better than inflation. They solve some of the problems that inflation faces, but then they have other problems of their own. So let me now go to the meat of the talk, and I think I don't have much time, so let me just go a bit quicker here. So the Bfss matrix model was developed by these gentlemen in 1997. This is a model of matrices. This is a model of quantum mechanics of matrices. So this is just a quantum mechanical model. As you see, this is just time parameter, nothing else. And these are bosonic matrices at the x's, and then you have fermionic matrices. There are 9 bosonic UN matrices, and there are 16 fermionic superpartners. Now, these are n by n matrices, and this is the n of the UN that appears here, the capital N. A similar model was developed by these gentlemen in Japan, known as the Ikkt Model, and this is not even a quantum mechanical model. So even the time parameter goes away here, and you just have bosonic and fermionic matrices, and an action corresponding to that. So why am I showing you these matrix models? Is because the Bfss model is supposed to be a non-perturbative proposal for M theory, whereas the Ikkt model is supposed to be a non-perturbative proposal for type 2b superstring theory. Now, what do I mean by that? And I don't want to get into details of this, because matrix theory is a topic on its own, and I'm not a string theorist, I'm not an expert on this. But the idea is that you look at this very simple quantum mechanical model. I mean, irrespective of how complicated it looks, this is still a quantum mechanical model, not even a QFT. You can calculate certain objects in it. For instance, you can calculate, some amplitude in this quantum mechanical model. And what is remarkable is that that amplitude gives you the amplitude of graviton scatterings from M theory, or graviton scattering in supergravity, essentially, which is the low energy 11-dimensional supergravity, which is the low energy limit of M theory. So you can calculate quantities in these matrix models, which remarkably reproduces much more complicated calculations in its string theory counterpart. And in this sense, I mean, there are many different, rigorous ways in which one can do matrix regularizations of world volume actions in order to derive this and show that these are indeed have a very close connection to string theory, if not they are the non-perturbative definition of string theory. So the idea here is that this is an n equals to, so let's look at the Ikkt model. This is an n equal to 2, d equals to 10 model. As you can see, there is no metric here. There's no, this mu's and nu's are just given by eta mu nu. So there is no g mu nu here. This is just a flat metric. There's no dynamical metric here. So where is space and time? And space and time are given by the eigenvalue distribution of the bosonic matrices. And the way to see this is because supersymmetry is realized by a relation like this. And supersymmetry in this case is a relation between space and time, because this is local supersymmetry, this is supergravity. And this is realized by the eigenvalue distribution of bosonic matrices. So the eigenvalue distribution of bosonic matrices gives you space-time. I will go into a little bit more detail about this later on. So just to give you a heuristic picture, the emergent geometry is this. The diagonal element of these bosonic matrices gives you the positions of d branes, so-called d branes. So those give you the position of space and time. And the off-diagonal elements tells you about strings which are connected between these d branes. So if the d branes are very well separated, then the off-diagonal elements are very close to 0, because it takes a lot of energy for the strings to be connected between the d branes. So well-separated d branes means these matrices are more or less as diagonal as possible, and then the diagonal elements gives you the position of space and time. This is, remember, 9 plus 1 dimensions. I'm not doing a toy model of 3 plus 1 dimension. So this just tells you 9 spatial dimensions and 1 time direction would emerge from this model. So this is not, as you can clearly see, this is not some EFT. This is some dual description of matrices which must take over at some UV theory, and I must have classical space-time emerge from it at large separation between these d branes. So at some low energies, I must have smooth space-time emerge from a very exotic-looking Lagrangian like this. And that's what I'm claiming, or what I'll show you does happen. So there is a lot of rich promise of UV complete description cosmology in this kind of a top-down approach from a non-perturbative description of string theory. Okay, so how does this happen? And first, I'll talk about the background dynamics of this Ikkt model, which was carried out by this Japanese group led by Jun Nishimura. So none of this is my work. This is mostly numerical. And I'm just showing you this to give you a heuristic understanding of what happens. So what happens is that you have 10 of these matrices and you diagonalize the A0 matrix. So remember, A0 is supposed to be the time matrix in some sense, and the AIs are the spatial matrices. The UN symmetry allows you to diagonalize one of the matrices. So you diagonalize the A0 matrix in a way that the diagonal elements keeps increasing in magnitude as you go down. There is some technical requirements of IR cutoff so that the matrices are not infinitely large and so on. Those are not important. What is important is that then you define time through a coarse graining. The coarse graining is that you take some little n and you average over little n amount of these eigenvalues. The remarkable part is you evaluate this path integral just numerically. So there's nothing else that goes in except that the A0 matrix is diagonal. And if you evaluate this path integral, what you find is that the spatial matrices, this 9 AI matrices, acquires a band diagonal structure, which means that this small space in here is little n by little n. Remember, the full matrix is big N by big N, but only little n by little n is non-trivial. Everything outside goes to 0. Everything outside falls off to 0. This is not something that would happen unless you have a very specific Lagrangian like this. So if you just start with any Lagrangian, any SUN matrix and Lagrangian which obeys an SUN symmetry, this will not happen. This is something very specific for the Ikkt model that you get this band diagonal structure. Why is this important? Is because then you can plot the eigenvalues corresponding to these nine spatial matrices. So you essentially define some moment of inertia tensor. This is just an order parameter. And you can plot 9 eigenvalues. What you find is that 3 of the eigenvalues becomes large at some critical time. Again, remember this time is something that I defined over here through some coarse graining. As you go down, the time increases because the eigenvalues increases in magnitude. These are all positive, by the way. That's also something that you can do because there's a SUN symmetry. And the point is that at some critical time, these are all numerical results. You find that 3 of the eigenvalues become large and the rest remain small. And this is the crucial finding, that you are not compactifying space-time on some Calabi-Yau manifold like you have to do for most string B models like KKLT and so on. In the Ikkt model, the emergence of 3 large spatial dimensions. So all the eigenvalues are small to begin with, and these are the eigenvalues corresponding to spatial directions. Only 3 of them become large at some critical time. The rest remains small. So there's some dynamical mechanism through which you have 3 large eigenvalues and the rest remains small. And of course, that means that the extent of space parameter, this is something that's related to the scale factor, for instance, in standard cosmology. This becomes also large at some critical value. And this is the takeaway point from the background dynamics. Since I'm running out of time, let me skip over a little bit to say that the take-home message is that, sorry, go ahead. How much time do I have?
Somebody asked a question.
Oh, yeah, go ahead, please.
Saurabh, are you able to ask the question? Yes, I think it's in the chat box, but
okay, let me try to find the chat box. How are these matrices related to each other? Yeah, they're not related at all. You have 9 matrices, and they're just related in the sense that they're related through the Lagrangian. That's their only relation. There's nothing else. Does that answer your question? Okay, I think that does. I got a thanks. Okay, so you have SOn, 1 symmetry to begin with, and you end up with SO3, 1. This is a dynamical spontaneous symmetry breaking without requiring, without doing this by hand. Why is this happening? The reason this is happening is because the A0 matrix is diagonal to begin with. How much time do I have? Sorry.
About 15 minutes.
Okay, I'll finish in 10.
Okay.
So the A0 matrix is, I have made this to be diagonal by definition. So the first, if you look at the Lagrangian again, in the Lorentzian matrix, sorry, in the Lorentzian model, this and this has opposite signs. So the A0 has some opposite sign corresponding opposite to the AI, AJ. So the first 2 terms have opposite signs. What it means is that the A0 is diagonal. So this term tries to diagonalize the AI matrices because A0 is diagonal by definition. Whereas the AI, AJ, because these are SUN matrices, this term is maximally non-commuting. So there is a competition over here. Like, this is a maximization problem. One term tries to diagonalize the AIs and the other term tries to make them maximally non-commuting. You can solve this problem and you find that this is solved by the Pauli matrix structures. So you have the 3 Pauli matrices and the rest are 0 or very small. And that's why you have 3 large dimensions. This is not the full story, of course, because Pauli matrices give you a fuzzy sphere, not some smooth space-time. And this is obviously some heuristic understanding. I'm ignoring the fermionic matrices, and those are important. I won't go into the details of this because I don't have so much time. And these are, again, all numerical values, numerical estimates. But what you can do is, beyond the Lorentzian model, one can, even in the Euclidean model, calculate things like the free energy. Again, you have an action, you have a path integral. So you have a partition function in the Euclidean model, and you can calculate the free energy. And what you find is if you calculate the free energy for d equals to 9, 7, 6, 5, I'm just showing you 7, 6, 5 because I couldn't fit everything on the same plot. You find that the free energy is least for d equals to 3. And this is not linear. For d equals to 2, again, it's much bigger. So there are multiple indications that once you include fermions, which is again essential, d equals to 3 is somehow preferred, even though you start with a much larger spacetime. You start with 9 plus 1, but d equals to 3 is somehow preferred, not just through this dynamical mechanism, but also if you just calculate simple things like free energies. And this is a remarkable feature of the Ikkt model, which again, I should mention, none of this is my work, was found out by this Japanese group over 10 years now. They've been working on this. Okay, so what are the takeaways from this part? That there is some numerical results which show that you have spontaneous symmetry breaking from SO9 to SO3 at some critical time. This is very similar qualitatively to the dynamical mechanism of string gas cosmology. In string gas cosmology, Waffa and Robert Brandenberger, they showed that even though you start with 9 plus 1, there is some heuristic dynamical mechanism which takes you to 3 plus 1. And we are finding something similar here. Here, the arguments are not so much heuristic, but rather numerical and, I would say numerical. The horizon problem in this case would be automatically solved because smooth spatial space-time is emergent here, right? Time is also an emergent quantity. So causality by itself is emergent in this model. And remember that, as I will show you in the next slide, the initial thermal state of quantum mechanical matrix model automatically would generate correlations over the entire emergent spatial section. So this statement is, I'm sure, is not clear now, but it will be clear, I promise you, in the next slide. Now, what is important is that the preliminary numerical results show us that 3 large dimensions you have, they do not give you exponentially expanding spacetime. So that would be a microscopic model of inflation. But so far, numerical results do not show you that you have exponentially expanding spacetime for the 3 large dimensions. But nevertheless, we have an alternative for an early universe scenario, which is UV free. And why is this UV free? Well, that's simple, because the eigenvalues of the matrices are never trivial. They never go to 0. As you go back in time, they are small, but never 0. And because the eigenvalues tell you, they are in some sense a measure of your spatial indices, that just tells you that if you go to t equals 0, all the eigenvalues don't go to 0. They are very small, but non-zero. So that just means that you don't have the Big Bang singularity. Now, another operational way to understand this is because this is a quantum mechanical model. This is not QFT. So there is no object you can calculate which would diverge. There is no problem of so-called renormalization in this model. This is not a quantum field theory to begin with. So the non-geometric phase at some critical time gives rise to some standard, Big Bang cosmology after the spontaneous symmetry breaking. However, we have no analytic control over the expansion of space. These are all numerical results. This just tells us that we go from 9 small dimensions to 3 of them becoming large. That's all we know. We don't know. We can't write down an equation for that yet. This is just numerics. And this is the takeaway, as I've already mentioned. I have a 3 plus 1 dimension universe emerging dynamically from some non-perturbative matrix model description of superstring theory. Now, to make this more concrete and make connections with observations, we really need to go beyond background calculations and numerics and, go to cosmological perturbations. To do that, we need to go beyond the Ikkt model. What we would do is take a state in the so-called Bfss model such that the background evolution is given by the Ikkt model, as I just showed you, while the primordial perturbations are in a thermal state. Now, this is the crucial point here. I'm introducing a lot of new ideas today about string theory and cosmology and so on. this is not a new idea. This is not an exotic idea. Because people are so familiar with inflation, they think that the initial state must always be given by some quantum vacuum. That is not necessarily true. There are a lot of cosmological scenarios, such as string gas cosmology. Even in inflation, there are these models of warm inflation, which requires that the initial state is given by some thermal state. And all we are saying is that the initial state here is going to be given, of the cosmological perturbations, is given by some thermal state. That's my only requirement. Now, why is this possible? Is because this is something that it will be familiar to any string theorists in the audience. If we start with the Bfss model and we go to high temperatures, in particular, if we compactify on this thermal circle, then we regain the Ikkt model. So at temperature going to infinity, we go to the Ikkt model starting from the Bfss model. Now, in the early universe, if we are saying that the primordial perturbations are in a thermal state, and it's very natural to assume that, because if there is no inflation to dilute the temperature, so to speak, so there's no exponential expansion, then the temperature was very high to begin with. If the temperature was very high to begin with, it is only natural to assume a thermal state. As I already mentioned, thermal fluctuations are considered not only in string gas cosmology, but also in models of inflation, like warm inflation. And again, standard quantum vacuum fluctuations is not a monopoly of inflation, but also in pyrosis. So this is just two different kinds of initial states. And I'm just choosing the thermal state. It makes sense physically because now I don't have inflation, so the temperature was very high to begin with. If the temperature is very high to begin with, we should assume a thermal state. And given a thermal state, there's a standard way to calculate the power spectrum of scalar and tensor cosmological perturbations. I won't go into the details of this, of course. This is found in this nice paper from 2005. So what am I telling you is that given some thermal partition function, you can calculate the specific heat and essentially the free energy and the internal energy, and then from that, the specific heat and so on. And using those quantities, you plug it into this formula and you can calculate the power spectrum for scalar and tensor perturbations. That's the idea. I won't go into this detail of operator interpretation. That's something I'll leave for now. So what we want to do is we want to calculate the thermodynamic quantities for the Euclidean Bfss model and expand in this high temperature limit because we are in this high temperature. This is the only free parameter I have in the theory. If I do that, this is again simple. This is just a quantum mechanical model. I'm expanding the fields. Remember, the fields here are just matrices, so I'm expanding them in this Matsubara frequencies. And if I do that, I can calculate the free energy and I go to next to leading order. So that's why I must go beyond Ikkt and I have to go to leading order is just Ikkt. I need to go to next to leading order. What is remarkable here is that this chi1 factor is proportional to the extent of space parameter that I showed you earlier in this numerical plots. Now, as I mentioned, I don't have analytic control over the extent of space parameter. Nevertheless, I don't really need that. I'm just showing this as an arbitrary function of time. This is all I require, is that the extent of space parameter shows up in the formula for the free energy. If that shows up and I plug the free energy into this formula that I had over here, so I just plug the free energy in this formula and I want to calculate the scalar and the tensor power spectrum. That's what I want to do without going into details. What I find is the following. I find a scale invariant spectrum for the infrared modes of observational interest. So I find that the scalar power spectrum scales like this. It's scale invariant and the amplitude goes like this. And this is the string scale and this is the Planck scale. So this is the ratio of the string scale to the Planck scale. And that is essentially the same. I mean, if you calculate this given the standard estimates for the string scale, you find a 10 to the power minus 9 number that you require from cosmology. This is remarkably similar to what one finds in string gas cosmology. That's nice because that's another approach of cosmology coming from string theory. And this is what we find. And again, this is very non-trivial. This is not something we could have manufactured. I don't have anything to play with. I just calculate the free energy. I plug it into the formula and I calculate what is the power spectrum. And it turns out that the power spectrum for the long wavelength modes of observable interest is exactly scale invariant for both the scalar and the tensor modes. What is even more satisfying is that the UV modes, things which we don't observe, the power spectrum for the UV modes for the scalar power spectrum corresponding to the UV modes is not scale invariant. It gives us a Poisson spectrum. It's proportional to k square. This is a distinct prediction from inflation. Unfortunately, they are not of direct observable consequence because we can only observe the long wavelength modes, and those are scale invariant like for inflation. However, this can have some indirect observable consequences. Now, a small tilt from next to leading order corrections would appear, and that would what is known as the NS value, the tilt value in cosmological observations, would come from the next to leading order. Now, the exact time dependent, as I mentioned to you, I don't know the exact time dependence of this chi1 parameter, but I did not need that. That just cancels out of the final expression in a beautiful way to give me a scale invariant spectrum. So this result is robust, irrespective of my ignorance about the analytics of the background. The tensor to scalar ratio, this is another quantity that is of primary interest to cosmologists, is given by something like this. This alpha parameter is something that we are calculating. We haven't calculated it yet. This is something related to the off-diagonal pressure perturbations. And this is going to be something like a 10 to the power minus 3, 10 to the power minus 4 number. So this is not something that we fine-tune to be 10 to the minus 34. And, this is not 0 or something like this. But this is something that we are working out. We should be able to find this, in a couple of months, hopefully. So just to give you the final summary, we haven't worked out the background dynamics yet, right? I just showed you that the background dynamics is some numerical thing. I don't have analytic control. If you contrast this with inflation, this is like saying that, in inflation, people still don't know exactly what happens in reheating, and yet we are able to say with confidence that inflation predicts a scale invariant power spectrum. Something similar is happening here. We don't know exactly the analytical dynamics of the background expansion, and yet we are able to say with some confidence that we have a scale invariant power spectrum. And that's quite unexpected and remarkable. And this is something that is really coming out of the theory. This is not like inflation that you have a potential to play with. I have nothing to play with here. As I mentioned to you, the temperature is a free parameter, but the temperature also, cancels out of the final expression. So even if the temperature was there, that would affect the amplitude. It would not affect the fact that I have a scale invariant spectrum. This is a completely top-down derivation of cosmology coming from some string theory. So I conclude here, and this is my last slide. So it has been notoriously difficult, as was mentioned already, that to find accelerating solutions in string theory. This has been very, very difficult. I am working to find out some explicit derivations from M theory for some short-lived de Sitter vacua. And we worked out that, we haven't worked out inflation yet, but we have worked out that de Sitter might exist as a coherent state over some warped Minkowski vacua. So vacua is warped Minkowski, but some coherent state gives you some de Sitter interpretation. And very recently in a PRL, like 5 months ago or so, we worked out that, this has a lot of consistency rules, which rules out sort of bouncing models and things like this, even though it allows for de Sitter. So we have to work out what it means for inflation. And this is something that I'm doing with string theorists at McGill and also at Liverpool. But irrespective of that, what I presented to you today is a new path towards the UV complete paradigm for the early universe. This is very ambitious. As I showed you, start with some matrix model and try to derive some cosmology from it. But hopefully I've convinced you that this is promising and this is exciting and there's a lot to be done. We need to figure out the analytic control. We need to figure out the details, the analytic details of the non-geometric phase. What are the connections to non-commutative geometry? There are some connections which have been worked out by these people with these matrix models. We have to make this more explicit. What are the connections to, what are the details of this spontaneous symmetry breaking? What are the connections to string gas? We again have some preliminary results which show that, the pressure is equal to 0, exactly as in the quasi-static phase of string gas. So there's some connections with string gas, but we have to make this more rigorous. For any string theorists, we need to figure out what is the connection to matrix string theory. Again, this is something technical. So if you're not familiar with this, don't worry about it too much. But there's a lot of interesting aspects also for this from the string theory point of view. And finally, from cosmologists or observational cosmologists, we have to work out what is the non-Gaussian signature of this model. We have to work out this alpha parameter to get an exact value for the prediction for the tensor to scalar ratio. And we are working on this. There's a lot to be done. I think this is very exciting, but nevertheless, hopefully I've convinced you and this excitement will rub off on some of you. Thank you so much for your time. I'll stop here.
Does anybody have any question?
thank you so much for a very nice talk.
Thank you. Thank you so much for your attention.
Yeah, I would just like to ask a nice question. I saw that you gave an expression for the free energy from which you calculated the things that you are after. So,
That's right. That's right.
Yeah. So that free energy is actually the free energy of the Ikkt model.
That's right. It's actually something more. It's the free energy of the Bfss model at high temperature. If I take the temperature to infinity, it will be the free energy of the Ikkt model. So I just go to the next to leading order. So it is the free energy of the Bfss model calculated to next to leading order. So it's Ikkt plus something.
Okay. So just then you also mentioned that you don't have an analytic control over the Ikkt model and also the Bfss.
That's
model.
right. That's right. That's right.
So can you just state a few steps by which you can actually analytically calculate the free energy?
Oh, that's right. So okay, good. So what I mean is that I don't have analytic control of these matrices as functions of time as emergent in the Lorentzian Ikkt model. That's what I don't have. What people have tried to do is take the Lorentzian Ikkt model and do some numerics. Even for the Lorentzian model, you can't even do Monte Carlo. You have to do something more. And I'm not a numerics person, so I don't know the details, but you essentially have to do something like this lunge of a complex, lunge of a method. Now, that would tell you how do these eigenvalues, which I said represent space, emerge or dynamically evolve as functions of time. That I do not have. However, I can take the Euclidean version of these models and still calculate the free energy. That I can completely do analytically.
I see. Okay. So the thing is that you said that from the eigenvalues of these matrices, you find that out of the 9 possible things, 3 only emerges out.
That's right. That's right.
Okay. So these 3 are the specials. These 3 you identify with the spatial directions. Is it?
Yes. Yeah, so I'm saying that the 9 are all spatial directions, but they're all small to begin with. At some critical time, 3 becomes large.
Okay. And what about the time direction?
Right. So the time is the A0 matrix, and I am diagonalizing it to begin with. So that I'm just saying the A0 matrix is diagonal. I can do that because I have this UN symmetry, and I'm diagonalizing it to begin with. So that's something that I'm doing from the beginning. That's right.
And it is with the Lorentzian signature to start with. You're working with the Lorentzian.
That's with the Lorentzian signature to start with. I mean, again, this is not my word, but yes, the analytics. The numerics were done in this way. Yes, that's right.
Okay, thank you.
So part of the idea here is that in any string model of cosmology or de Sitter space, in most string models, so the one that I talked about very briefly in the conclusion slide, that is somewhat different. In that, what we found is that the internal dimension. Let me give you the standard paradigm of, let's say, KKLT or something like this. You just say that your internal manifold is some constant, and you compactify on some Calabi-Yau space, and then you have 3 large dimensions, and that represents some cosmology, whereas the internal dimension is just some constant Calabi-Yau space with constant volume. What we found out is that if you try to do this so now let's forget about this matrix model approach. If I try to do this from this M theory approach that I just very briefly mentioned at the end, you find that the internal manifold cannot be time independent because the fluxes cannot be time independent. So what has to happen is that the unwarped volume has to be time independent, but the warped volume is not. So that's what we found, which means essentially is that the internal manifold is not Calabi-Yau. It's something much more complicated, essentially. So there's a lot of consistency checks, like if you put some fluxes on some space, on some compact space, then it must satisfy Gauss law. So things like this must be still satisfied even if the space is dynamical. So that's very, very difficult to show that all of these things cancels out and it is still true. And we showed that this is true. So I think that the matrix model is another way of finding the same result. So in that case, we really started with the M theory Lagrangian. So we took the M theory dual of type 2B, what is known as, and we derive a cosmological dynamics allowing for time-dependent fluxes, time-dependent internal manifolds, and so on. And in this case, what we are saying is something else. We are saying that there's a matrix model which is also the same as M theory in some dual picture. And again, what we find is that the internal space-time is dynamically compactified. So there is some synergy here. I'm not trying to argue that I have a rigorous mathematical proof of saying that both of these things are the same. This is something that we want to work out. But the difficulty is because we know so little about non-Calabi-Yau spaces. We almost know nothing about non-Calabi-Yau spaces. I mean, I know nothing about any of these things almost, but even string theorists who work on this know very little about these things. So that's why it's difficult to make progress. But the idea is that the matrix model is giving us some dual picture of what we already found in the M-theory language. That if we take the M-theory Lagrangian and we try to see if I want to have the exterior dimension to be de Sitter, what must the internal manifold be? And we already found that has to be non-Calabi-Yau, that has to be dynamical, and it has to satisfy this flux quantization rules of Witten very, very non-trivially, not at all in the way that, for instance, KKLT does. So that's where I think all the fun lies, so to speak. And it's very challenging, but there may be, and maybe there's a synergy here. The matrix model is also telling me the same thing, but in a different way.
Okay. I think if there are no other questions, we should thank the speaker again. And thank you, Suddhasattwa.
Thank you so much.